Okay, Assalamualaikum, good evening, good afternoon. Okay, really sorry because I thought I already share with you the link, but when I open the Zoom, nobody around. So, okay, that was my mistake. Sorry, okay, now we have about 27 for 25 participants. 20, yeah, more is joining. Okay, anyway, okay, for tonight, since as I already mentioned during week 10, okay, just before the test, okay, or the week before the test, I did mention that you are going to have a project, okay? It is a mini project. I will give you a brief introduction on what's need to be done for today, okay? The so-called the final instruction is not ready yet. I will try my best to upload it by tomorrow. Okay, you can check tomorrow after 5. It should be in the Putra Blast. Okay, I will share the detailed description on what need to be done. Okay, for example, for a report, what need to be you know, the element of a report. Amin Faid dah macam hantu dah tu. Memang gambar live ke apa ni? Okay. Okay.
Tak live.
Okay.
Ni baru live.
Okay. So for the report, yeah, as you already familiar because before you join UPM, you already done lab report during your high school, during your matriculation, your A level, and so forth.
Até assignment 1, creating to class.
Said, okay, I will mute you. Okay. Okay. Anyway, for the report, first, of course, you will have a front page. Okay, front page. Then you will also need to have some motivation on your introduction part, the objective, motivation, objective, and the scope of work, okay, that need to be carried out, and some theory that related to the dynamics, okay, of course related to the dynamics, and something that is moving, okay, something that is moving, and okay, something related to the dynamics, either body dynamics, particle dynamics. Particle dynamics, for example, that you would like to design your own projectile using water rocket, for example, right? Now I think you know how to calculate the height, the trajectory with the water rocket. But you need to combine knowledge, fluid mechanics a little bit with this subject, because you need to calculate how much pressure. For example, last time we used like 30 psi, 30 per square inch. Okay, 30 psi. Then you need to convert that with that given area at this. I think it's not, if not mistaken, it's around 15 mm diameter of that particular cylinder. Okay. the PVC pipe, yeah. The inner diameter of the PVC pipe is around 14, 15 mm. And you know that the pressure is around 30 psi. And with that, you can calculate the force, because pressure is equal to force divided by the area, right? So area is pi r square, or pi d square over 4, same thing. So the diameter, you know, is around 14 or 15. You may choose. And the pressure is 30 psi. You need to convert into the standard unit, okay, Newton per meter square. Then you just multiply pressure by the surface area, the cross-cut area of that particular PVC pipe. Then you get your force. Okay? As simple as that. Okay? That is if you choose to design a mini water rocket, because we have done it last semester. And also, you can also design something like, I think I have some example. Okay, let me share the screen. Okay, like this one. This is a screw. Okay, when this part is you rotate it using your hand, what happen is this slider, this particular slider will move either to this side or that side. Okay, to the left or to the right, depending on the rotation, whether it is clockwise or anti-clockwise. So that this platform here can lift up something lah. Okay, you can have something like this, or where was it? You can also design something like this. Of course, this is look too complicated, but you can have something that is more simple like this. Okay, here you can have give some force from down here, down below. Then these linkages, it will, if you move this slider up and down, what happen is this particular pink color rod will flap like a flapping wing. Okay, so it's kind of many interesting design that you can have. Okay, and there are other design, for example, like where was it? Yeah, this one. A second. Like this. Okay. This is the power hacksaw. It is a saw, and it is just a wheel. And here there is a rod here attached to this particular wheel, and this point here is fixed. This one is also fixed. What happens is, if this particular wheel is rotating, okay, rotating either clockwise or anti-clockwise, what happens is this mechanism, the yellow color here will go left and right. What happened? Okay, we go. It will cut this material lah. purple color. And that's the thing. And for today, let me see. Okay, for this week, as I already mentioned last week, that we will move into these particular topics, new topics. Okay, planar kinematics of a rigid body, work and energy. And next week we will cover the impulse and momentum. And next week is week 13. After that, on week 14, I will cover the vibration, the introduction to the vibration. Okay, and that's all. Then we are finished with our syllabus. I think I didn't include for example, during our earlier weeks that we also have on the planar kinematics, okay, we didn't cover on the, for example, uh, uh, Earth trajectory or the Earth or the satellite motion relative to the Earth, okay, something like that. More like space mechanics stuff. But anyway, I will share 2 or 3 videos to cover on that part later on. Okay, probably next week lah on that. And this week, I will focus on these particular topics. I will share 2 or 3 or 4 videos. Okay, examples on these particular topics. And then we are done on these particular topics. I didn't spend more time on this part because of we already learned the concept of particle kinetics, and we solve it using the work and energy. And here we just use the same concept to analyze the rigid body. Okay, that's the only difference. And if you look to this particular okay, this screen here that I share, should you have any question, you can straight away type in the chat, or you can unmute and you can ask question. Okay, and on these particular topics, similarly like what we have covered earlier, that we know that the kinetics energy is like this, right? So it is half mv square. G is to represent the center mass. Okay, and then what's the main difference here is last time we only focusing on the translation of a particular particles. Okay, now when we are talking about body, you will also see that that particular body will rotates. Okay, it's not just translate but rotates, and therefore you will have this particular term. Okay, so oops. So you can see that this is for the translation, and here is the rotation. The only difference here is last time we only look into this as well. Of course, last time we look into the and also the potential energy, right? Okay. But now we have this term. This is also considered the kinetic energy. Okay. This two is belong to this kinetic energy because it is rotating. And I think Ishan or somebody did ask me about this part here. Okay. For example, let's say we have somebody, and it is the center of mass G, and this is rotating, right? Rotating, and the axis or the center of rotation is at point G. What happened is your I is equal to, if it is a flywheel, for example, okay, then the by definition is something like this, mr square. Okay, the r is of course this one point here, or you may call it as the radius of gyration. It is like this. But if this particular body, the axis of rotation is somewhere here, for example, okay, or here, or up here, okay, that's why we use the parallel axis theorem. Okay, for example, if the axis of rotation is here, A, okay, axis of rotation is here, meaning that this particular object here will move like that. Okay, orbiting this point A, okay, and therefore this term here you need to plus with m d square. D is the distance from G to A. It is just like that. Okay. If point A is the point of rotation, D is, if we learned last time, can name it as AG, something like that. Okay. RAG. It is the same thing lah. Okay, let's say the point of rotation for this particular body here is here at B. What happen is it will go like that, right? So if that is the case, then D here would be R, B, G, or the distance from G to B. Okay? Clear? Eh? Any question?
No, doctor.
Yeah. Okay. I think it is very simple actually, parallel axis theorem. That's why I didn't give a formal lecture. I would say this is a formal explanation, but if you look through the examples that I already shown, I believe you can get what does it mean. Okay. Okay. Now, of course, if okay, before I forgot, if the point of rotation is at A and here become, oops, IA lah. Okay, this is IA. But if the point of rotation here is B, then become IB. If here is our point O and this body is rotating orbiting this point O, then this is become IO. Okay, that's all. Okay, now since we are talking here we are talking about the energy, kinetic energy, because of that particular rotation, and therefore we will have this full term. It is here. Oops, should move it down a bit. Okay, this part here, it is from this, and it is multiplied by the omega square. Okay, and you know that V is equal to R omega. If you have this is just a flashback. I would say flashback lah. Okay, if you have a body like this, and this is the point of rotation at this point O, and you want to examine the let's say this is a point G, center of mass. Okay, point G, then you want to calculate VG. What happen is you must know the distance from point O to point G. What is the distance between these two? Okay, so you know your R, G, O, and then omega is the rotation, either counterclockwise or clockwise. Okay, if you are interested with if you are only interested on the magnitude, then either way is not an issue. But if you looking at the vector of it, then you might need to look carefully, because if you define it as counterclockwise, meaning that positive is in that direction, then if the system moving that direction, it become negative. So that's the only thing that you need to make sure. If you look into this book, it looks very scary, because too many things around. But my job is to simplify and to make it everything clear lah. Okay. Okay, now if you have a spring, the standard definition is like this. Okay, you have a negative sign here. The thing is, if, okay, okay, let me read this one. If a linear elastic spring is attached to a body, the spring force, Fs here, acting on the body does work when the spring either stretch or compress. Because spring have two types. Either the you can stretch to get the forces, or you compress it. Okay, there are two types of spring. And then to further from S1 to further position S2. S1 is here, S2 is here. Okay. In both cases, the work will be negative. Okay, work will be negative since the displacement of the body is in the opposite direction of the force. Because you know that the spring was designed to resist the motion, right? So in a way, at any time, it is you will have the the forces will not the same as the direction of the motion. Okay, for example, like okay, initially at point S, okay, unstressed position of the spring. Okay, it is originally here. The spring is here, but then you push it and it become compressed here, this point. Okay, therefore it will have a negative. Okay, why negative? You see, this is your, for example, this is your hand lah. You put your hand here. Okay, you push, meaning that this is the direction of motion, the force that you give it. Okay, let's say this is P lah. P. However, the spring here will resist against the force here. It will against. It will I will put it as here what is Fs. Okay, put it as Fs lah. Okay, Fs will try to resist these forces. So that's why it is a negative. However, if okay, however, if the spring is okay, if let's say the spring is here, okay, start at here, it is already being compressed, okay, already compressed, okay, so it will have some sort of potential forces inside this particular spring because it is already at that position. Then you release it. Okay. 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 If the spring is here, the potential force is, of course, that direction lah. Because if you release, it will go that way, right? So if you have a ball, for example, here, okay, a ball, football or any ball, tennis ball. If you put it here, you release this spring, and this particular ball will move that direction. The spring also will move this direction. The force, this work done here become positive. Okay, clear? Similarly, if the spring is start from here, is already being stretched. Okay, then you release it. So the same principle. Okay. And okay, I think through the previous example, you should notice that we also have something like this, right? In that particular example, if not mistaken, there is a wheel, and then there is a force P with something pushing, and this particular roller here will move that direction, and so on and so forth. But now here, what I'm trying to highlight here, when you have a wheel, something like this, the thing that you need to consider is the translation and the rotation of this particular system. Okay, the wheel will rotate. Okay, if the wheel is not slipping, okay, if the wheel slip, I'm saying slip, S-L-I-P, not S-L-E-E-P, not now. Okay, you should awake right now. Okay, sleeping. If the wheel is not slipping, meaning that it will rotate nicely lah. Okay, then you need to consider both the translation and the rotation. However, if the wheel is slipping, the wheel is not omega here is equal to 0. So what happened is, oops, this term here is 0 lah. Okay, we will go through example, then you will get what does it mean. Okay, if let's say we have a system, or let's say we have a bar like that, like this, and attached to a, you know, something like that, and then there is a moment m. Okay, so the work done, okay, um, okay, or sorry, not this one, the energy. So it's depend if you prefer to use U, then proceed. If you prefer E, because it is energy, you prefer E, then you can use E as long as it is consistent. Okay, E due to the moment, energy due to the moment, it is just simply m times the theta. Okay, the change of theta lah. Or to be more precise, it is the change of the theta. Okay, so m theta, that's all. Nothing nothing too complicated here. And yeah, don't forget, theta should be in radian. Radian. This theta should be in radian. For example, yeah, we have an example after this. So we go to that particular example. Yeah, this one. Okay. Otherwise, I need to think for something else. Okay. Here we have, sorry, too many. Just a second. Okay. On this particular example, we have a bar as shown here that has a mass of 10 kg and it is subjected to a couple moment of 50 Newton meter, and a force of P equal to 80 Newton. Okay, there are so many things appear here. So force which apply, and the spring has an unstretched length of 0.5 meter. Okay, if and then remain in the vertical position due to the roller guide at B. Determine the total work done by all the forces acting on the bar when it is rotated downwards from from theta equal to 0. What does it mean is, initially this particular rod here, this particular bar here is here. Okay, start from here, and the P here is pointing downwards. Okay, clear? This figure here, if you don't read carefully on this part, you might get confused. Okay, so initially it is like that lah. So what happened is, you know, let me redraw this part. This is the hinge where sorry, let me redraw it. Bar that, and there is a support lah here. And then, okay, first we know that this mass here, this bar has a mass of 10 kg. Okay, 10 kg. And if it is the shape is uniform, or the shape is the same, okay, then we can say that the center of mass should be at the center lah. Okay, center of mass should be there. The weight should be here. Okay, center. W equal to m g. And then so this is our m, this is g. So this is our weight lah. Okay. And what else? You know that this total length from A to point where we have this force here, this total length is 2 plus 1, which is 3 meter. And we know that W is at the center. Okay. And this part here should be 1.5 lah. That's why we multiply by 1.5. Okay. So this is the W times the perpendicular distance to this point of rotation, line of forces and the point of rotation. So that's why it is 1.5. So you got this value lah. In joule, Newton meter. So here why the work is positive. Why it is positive? Okay, as I mentioned earlier, we consider it as positive because of similarly like the spring. You know that this weight here, the weight is going down, and the whole mechanism is rotating this way, right? So the same direction. Okay, so it is positive lah. Based on the direction lah. Okay, moving on. Here we have a moment as well. Look on this. Okay. Just a second. Let me. I may need to delete this one. Okay. Where was it? Okay. Okay, now we are on the same page. Okay, now just now we look into the weight. Okay, and don't forget that we have another 3 items that need to be considered. The moment here, the spring, as well as this external force P, which is 80 Newton. Okay, so we move on with the moment. As already mentioned earlier, that for the EM, EM moment, or UM, the same thing. It is equal to M times theta. Okay, and here you have your M, 50 Newton meter, this one. And theta is, it is mentioned up here that it has rotate downwards from theta equal to 0 degrees to 90 degrees. Okay. Here it is pi over 2 lah, because, okay, For a complete circle, okay, for a complete circle, it is 2 theta, which is equal to 360 degrees. Okay, theta is equal to 180 degrees. Theta over 2 is equal to 90 degrees. Okay, and here it is 90 degrees. So theta over 2 lah. Okay, if you want to multiply, make sure it is in radian. On the left here is in radian. On the right hand side is in degree lah. Okay, don't forget that one. If you multiply with degree, then the value is become 1000. Okay, yeah, very big. Value become very big. So now we know that due to the moment, this is the energy that we have. Okay, moving on. If we look into this F here, this F is from the spring, Fs for this particular spring. Okay, we have Fs due to that particular spring, and it is pointed upwards because it will resist the motion. Okay, so therefore you will have a minus sign here. No worries, whatever item inside this part, I will explain it on this part here. Don't yeah, you know, it is quite long, so it's quite scary to see. But anyway, US, or I prefer to use E spring lah. Okay, it look like Pinocchio here. Okay, ES is equal to half K. I don't know why my pad, the sketch pad here is not that good. Kx square. Okay, it is the standard definition of it. And as I already mentioned, that the force here is resist the motion. Okay, so therefore you will have a minus sign. So K is given up here. K is given 30 Newton meter. Okay, we know K is 30. What is the value of X? Okay, so half, this should be 30. X is, okay, you know, unstretched length is 0.5. Okay, if you don't do anything to that particular spring, the spring will have a length of 0.5. Okay, if you put the spring on the table, for example, it should have this length. Okay, and there are some errors actually on this particular figure because this dimension should not be here. It should be they should redraw it with something else. Okay, if you look into this example on your own, I think most of you might really confused. Okay, I spent about half an hour just to understand why these two is related. Okay, okay. Okay, if you refer to this particular image here, okay, initially, the spring is like that, right? The spring is somewhere here, and this distance is 2 meter. Okay, 2 meter from A to point where we have our spring attached. Okay, 2 meter. So it is 2 meter. And this length here is 50. Okay, if you look up here, oh sorry, 0.5 meter or 50 centimeter, the same lah. 0.5 meter. Okay, and what happened is this thing is rotate this way 90 degrees, and it will be down here. Okay, and the point where we have our spring is, oh, it's really hard to draw it. Should be somewhere here lah. Okay, I can't put it. This spring here. So the spring, because if you see up here, this B here, it can move that way. So this B here will end up here. B will be here because this is pushing downwards. Then this spring will move to this position, point B here. Okay, and therefore the spring here will move that way to here. So here is, oh, okay. What happened is the spring is stretched up to this point, and we know that it is 2 meter, and it is mentioned that when that particular things happen, okay, as this is rotate, this length here is changing to 0.75. Okay, 0.75. So now what you can see is the original length here, the original is 2 plus 0.5. The final position is here is 2 plus 0.75. Okay, here it is 2.5. Down here is 2.75. So if you take the difference, okay, take the difference, you will have a 0.25 here and this one. The final and the initial unstretched. So this is the change of the spring length. I don't know why the book is like this, but it has to be, my comment to the book is they need to reproduce the image so that people will get it more easily understood. Okay. Okay, and oh, sorry. La ilaha illallah. Apa yang sebab ni?
Doctor, the
Ya.
initial
Sorry, Chan. I think I'm a bit sleepy now. Okay. Sorry, yeah. Should be like that. Okay. 2.25.
doctor, maybe because
Yeah, this one.
initially it was 0.5 and
Yeah.
then it became 2.75.
Yeah, this part up here. Okay. Initially was 0.5. It is a final. Okay. And the difference is 0.25. And you must also consider the length from this point to the point of action lah. And that's become 2.25. Okay. Just now, okay, I did a mistake because of I took this length here. It will not, it should not be that way. It should be only 0.5 because we are talking about the y direction. And here should be 2 plus 0.75. Okay, so the difference between this one is, yeah, it is 2.75, and the difference is 2. Okay, the difference is you just take this 2.75 minus 0.5. Okay, then you get 2.25. Okay, sorry, we should look into the vertical direction. Okay, so that's why then if you put it that 2.25 into this 25 here, it should be the same. Why this minus 0.25? I'm not so sure. Why it is like that?
Doctor, the main equation was something like half ks2 square minus half ks1 square.
Yeah. You know, this one, here we have 2.25. Where does this come from actually? Why? If the spring is stretched,
Doctor, it should be 0.5.
okay. Now we get it. When the spring, okay, at initially, when theta equal to 0 degree, here it should be 0.75. Okay, here should be 0.75. And if you want to take the differences, then you minus the unstretched length, which is 0.5. Then you will got this value. Okay. Okay, I missed that one. Okay, clear? So that's why you have this part and this part lah. Okay, by inspection, the spring does negative work on the because in the opposite direction to the motion or the displacement. Okay. Anyway, we move to the next or the last part here where we have the external force P. This one, and it is very straightforward. Okay, and we know that as the bar moves downwards, the force is displaced through a distance of pi over 2. Okay, as I mentioned just now, this is the theta, okay, and it is the r lah. Okay, from here to this point here, theta. The work is positive. Why? Okay, the work is positive because of the direction of the force is the same as the motion, direction of motion. So you have a 377 joule. Okay. And if you put everything together, this is due to the work, this is due to the moment, this one spring, this is the force P. Okay. Work, oops, let me scroll up a bit. This is due to this part here, W, work, weight, okay, weight. This one due to the moment, and this is due to the spring. Okay, negative because of resist the motion, not the same of the the direction of the force is not the same as the rotation here. And then the P here is this one, the external force. And that's it. Okay. Okay, done on this particular example. This one is it is a very straightforward where you have a spring and you have this system is more simpler than the previous one. Okay, you have a spring. This is the wheel or this. Okay, 30 kg. Sorry, 30 kg this, and you have a moment as well. So on this particular problem, there are two items lah, the spring and the moment. Does it mention that must rotate to it? Okay, from there. So only these two parts lah, moment and the Fs. Okay, we have the moment. Don't look for everything, but I'm trying to push you to focus on the main dishes. Okay, the main dish of our dinner plate tonight. Okay, this is the moment. Okay, moment, and we have the forces. Of course, in the books, it will go stages, but for me, I will look into the main ingredient first, then we will see what need to be add on. Okay, and this part, we have a moment, and the why I'm saying like that, because in real world, when you are facing when you are designing something, you will not start with these steps. Okay, you will not like that. You will see what you have in front of you. Here you have a spring, then you know that this mechanism here, the wheel, have a certain torque or moment. Okay, 5 Newton meter. So we start from there. That is the real world. Okay, now we know that by the principle of work and energy, we look into the kinetic energy, T1, and then whatever other energy involved. Here we also have the potential energy on this part here, okay, Ks square, and also the final potential energy. Okay, and now because in this particular example, it is mentioned that it start from rest. Start from rest meaning that T1 is equal to 0 lah. Okay, T1 is equal to 0. And then we know that M here is given 5 Newton meter, and theta is something that we need to determine. Okay, determine the angle through which it must rotate to attain an angular velocity of 2 radian per second starting from rest. So we need to get this angle lah. That is the theta. And what else? Here we have the spring, which is resist the motion, so it is negative. Okay, so it is half Ks square, and K is given 10 Newton per meter. That's the value of K. And then S, we have theta times the R. Okay, you know last time to get this, the circumference S is equal to 2 pi R, right? 2 pi R. However, if let's say you only have a certain not complete circle, so what happened? The S here will be, this is our theta. So become theta r. Okay, got it? Okay, and make sure that it is in radian lah. That's all. So that's why here you have a theta r. Okay, and then don't forget the square. This is my killer lah. I don't know, that is my weakness. When I press the calculator, normally if it is a square or whatever power, then I may tend to forget this part. So I hope you will not repeat my mistake. Okay. And on the T2, okay, T2, okay, that's become very a bit interesting. T2, how to get T2, the final one, the final when the, you know, when the this attain or get the speed of 2 radian per second, the angular velocity of 2 radian per second. Okay, this is the point where omega here become 2 radian per second square. 2 radian per second. Okay. If it is square, then it become alpha. Okay, be careful. Okay, now how to calculate the I/O? Okay, because as I already discussed before, that if you have a wheel or anything, and this is our point G, or in this case it put O, so let's change to O. Okay, this is our point O anyway. So I/O is equal to half m r square. Okay, because our center of rotation or the axis of rotation is this point here. So it is like this. But if it is somewhere else, let's say A here, okay, if it is A orbiting this point A, either this way or that way, then the I become, of course, you will use notation A, okay, make sure that this is our center of rotation, then it become half mr square plus md square. D is from here to here. Okay, clear? This is from the parallel axis theorem, this part. Okay. So for the in our case here, point O is here, and this is stay there. It's not orbiting something else. So we will use this equation lah. So here it is our M and it is our R lah. Okay, omega is already given, and we get this value. Okay, and then okay, after that, what happened is you will get this equation. Okay, on this particular equation, you have one unknown, which is theta, one unknown, and one equation. So you can solve this quadratic equation. Okay. Of course, you will have two values for theta 1 and also theta 2. So in this case, choose the smallest positive root. So the minimum value, so that you get that speed. Okay. Okay, I think that's all for tonight. There are a lot more examples that to cover. Tomorrow I will upload another a few more. Okay, I can't guarantee, but I'm sure I have two videos on example related to these topics, this chapter actually. So if you still have a question, you can text me, okay? Or we can arrange another session to discuss about it, okay? Specifically. So please, I think it's better for you guys to subscribe to my channel. I will not get paid for this job. You see, I'm not going into that. So it's just I don't have to remind you, because if you subscribe, by time I upload in the YouTube, you will get notified. That's all. There is a bell icon that you can see. Okay, good question. Okay, for the mini project, it is a group or individual. Okay, since you are away from the schools, okay, I would say schools. So you will do it individually. Okay, you will do it individually. And
Doctor, the
yes.
deadline of it?
Okay, the deadline is sometimes in week 14. Now we
Okay,
are in week 12.
12.
Okay, so you have about 2 weeks time. Okay, and
Okay, doctor.
okay, for me to evaluate your performance on this mini project, one is you need to come up with a report. Okay, the length of the report is something like 5 or up to 5 or 7 pages. Okay, yeah, but 5 pages lah, plus minus 5 pages. If you design it very compact, then you might end up with 5 pages. But if you put a lot of features, then it will go up to 7 or 8 pages. So it depends on how you rearrange it. And I think you already familiar on how to produce a report, because last semester we already done it on our project, right? For the CAT or engineering drawing class, so that you can have some idea on what to do. Okay, and similarly on this particular project, you need to come up with a paperwork, which is the report. And okay, I want to simplify your work because when you produce a report, it is for us as a lecturer, we want you to do presentation, right? And since we have these problems, you cannot come to UPM. So I want you guys to record your presentation. Okay, you can record. The most important thing is I want to see your slide of presentation. Okay, whether you can have your face together on that particular videos is up to you, but that is not compulsory. What is compulsory is the slide of your presentation or the whiteboard of your presentation. If you prefer to use whiteboard, then it's up to you. Okay, if you want to use a Microsoft PowerPoint or whatever software that you want to use, then up to you. And the narration, the voice should be your voice. Okay, not your parent voice or your okay, your loved one voice or whatever. So it should not be like that. So it is a individual project. The length of or the number of pages is around 5 to 7 pages. You can go up to 8 pages if it depends on your work. And the topics is open. Actually, the topics, the subject is open, but it must relate to the engineering dynamics. Okay, if the element of engineering dynamics is not there, then you won't get anything lah. Okay, you won't get anything. And on that particular report, there must be a drawing. Okay, I'm not talking about the detailed drawing as what we did in our class last semester, but not up to that level. But if you design something, the length, you know, the labeling of the mechanism involved, it should be there. Okay, should be there. The dimension, the basic dimension should be there. And then what else? Yeah, the free body diagram is a must. Okay. Last test, on the last test, I think many of you losing marks because you didn't provide the free body diagram. Okay. If you want to solve a static problem or dynamics problem or anything related that have a force involved, okay, then free body diagram is a must. Otherwise, I can't really see what is going on your paper. Okay, luckily, the exam question is, I'm the one who designed that particular question. So I know how to deal with that. So what happened if somebody else marking that paper and don't have any idea is what's going on actually, then it will have a big problem. Okay, so free body diagram is a must. And what else? Yeah, you need to do to have a conclusion, to show some working system. Calculation is a must. You must have a calculation to show a sample of a working model. For example, if you're designing a projectile, then you may need to show some calculation on the projectile that the for example the ball or bullet is project from one point to another point. Okay, so that should be there lah. References as well, if you are referring to any website, any articles, any videos, okay, so books even, so should be mentioned clearly in the reference. And other things that related lah to that particular project. The detail is, I will give it to you, the detailed description on what to do, on how the mark is calculated. Okay, for let's say you do this project, report is how much, how many percent, your calculation is how many percent, your mechanism, if the mechanism is working, if not working, how many marks, if it is working, then how many marks, your presentation is how many marks. Okay, talking about the presentation, because you need to record a video and it should be no more than 5 minutes. Okay, try to do that. Okay, a short video. I think if you have a slides, is around 10 slides. Okay, it's around 10 or 11, 12, something like that. 10 slides. So each slide is around 30 seconds. Okay, so try to make it 5 minutes, plus minus 1 minute lah. Okay, plus minus 1 minute. So between 4 to 6 minutes. Don't make it less than 4 minutes. If you do less than 4 minutes, I will give you a penalty. Okay, some mark will be deducted. If you go beyond 6 minutes, some marks will also be deducted lah. Okay, I want to make it short and sharp. Okay, no need to make it very lengthy without anything. So make it sharp and compact so that everybody can understand it. Okay, so videos, I think you are good with videos. Okay, I don't think you have problems on recording videos. You can use it using Zoom. You can use it using Microsoft PowerPoint. There is a function to record a video using Microsoft PowerPoint. If you don't know, Mr. YouTube is around. Mr. Google is around. Your friend is around. Okay. And there are a lot other platforms that may assist you to provide that. And for the report, you need to submit in a PDF format. So everything must be typed. Okay, not handwritten for report. Everything needs to be typed. Huh? Okay, any question before we end? I think about 10 o'clock now.
Doctor, we have to do the Katia designs, right?
If you want to, of course, you need to design something, right? You need to design something. If you are good with sketching, okay, your hand is gifted to do very nice sketching, and I can understand it very well. Okay, then you may even no need to go for CAD. But if you do using CAD, there will a bonus. Okay, there will be a bonus.
Okay, doctor.
Yeah. Any other question? You want to sleep? Okay. Farhan, Adam, Lukman, Izul, Yasvin, are you still around?
Yes, doctor.
Yes, doctor.
Okay.
Yes, doctor.
Yeah. Fazil, Haris,
Yes.
Aikal, Noreliza,
Yes, doctor.
Nur Faizah. Apa lagi? Start.
Doctor.
Okay. So, if you have further question, you can raise up in the WhatsApp group. Okay. And that's all lah. Okay. So the project is individual. You need to submit sometime in week 14, 2 weeks from now, and okay. Thank you. So shall we end our session tonight? Okay, and okay, we will end our session tonight. So thank you for your time. Have a great day. Have a nice sleep tonight. Okay.
Good night, doctor.
Stop sharing. Okay. Thank you. Okay. Bye bye. Assalamualaikum warahmatullahi.